Okay. Now, welcome to what will be a most unusual science class. First of all, I hope you can see that a little bit. This title, long and windy as it is the result of some rather down and dirty fighting amongst several departments at the university over the use of certain words. It was a real politically correct fight. Certain departments have their arms wrapped around certain words, and by the time I got done, this was what was left: the history of physics, cultural connections, and other issues, when I really wanted to just call this the culture of science. So we're going to deal with the culture of science under this heading, which is not all that bad, because to establish the culture of science, you actually have to look at the history of how science developed and what led to what we now live in, which is the culture of science. And part of this course is for you to talk with me about the science, the culture of science, and the culture in which you live. How many of you own cell phones? Come on, raise your hands, everybody. Okay. Is that not a scientific toy? Okay. You drive a car? Yeah. You have electric power in your house or your apartment? Okay. You breathe air-conditioned air living in Florida? Okay. What else do you have that's science-based? More or less everything. Okay. Otherwise, we wouldn't be here. So, for example, I'm going to tell you that if you want to keep track of this course, here's the website. It's a big, long string of stuff, but it comes down to the course number at the end. And you can track everything. On this website, I'll tell you in a moment, there's a bunch of good stuff for you to look at, and I recommend that you do, because it will give you more of the flavor of the course. It will also show you the schedule, and it will show you a little write-up that I prepared that'll kind of tell you where we are and where we're headed as we go along. This is my information, my phone number, my office. It's the spring of 2016, but don't let anyone tell you it's not spring yet, and all of that. So if you didn't understand anything I said, you're in the wrong room, and we'll move on. Okay, it's a one-unit course. This is what we have to start with, and it's not like any science course you've ever taken, because it's open for discussion. I mean, how many times have you taken a course where somebody says, Newton's laws are, and they put them on the board, and there's nothing to say. You know, you can't discuss them. They are what they are. However, something about Newton might be worth discussing, and we will learn that later. And other scientists were real people. They lived in a real world, and they had to deal with it. And you want maybe to understand what they had and how they interacted with the world around them, and how the world around them changed as a result of what they did. And the result of that is something that we can talk about. And we can understand the effects of their work and so on. So I want you to participate. See, there's a group of people participating. Okay? So you know, imagine sitting around participating. It reminds me of a quote by several famous philosophers, none of whom I can remember in their name, but it was said that it is better to ask a question and seem ignorant than it is to not ask a question and remain ignorant. So please, feel free to take part. If you really want to take part, we can meet on Thursdays at the same time, because it's pretty likely that the room is not busy on Thursdays at noon, and have some more open discussions if you wish. The website, this didn't get changed, but you saw the website on the first slide, so be it. Now, went too fast. Whoops. Oh, yes. All right, now, the schedule of the subjects that we will be considering. It's a little crowded because there's 14 things here. First, today, we're just going to talk about what is a culture. and what is the culture of science, and we'll talk about ethics, what can go right and wrong, some comments about pathological science and fraud, and give you a sense of what that stuff is. Next time we'll talk about how science got started. Some people say it got started with the first flake of a chip off a rock that led to a rock tool at the very beginning of human society. Then the Copernican revolution and the Newtonian synthesis. Prior to the Newtonian synthesis, one of the great scientific controversies took place, and it was the fight between Galileo and the church. So we're going to have to look at scientific controversies and see how they develop and how they affect the way science evolves, the way science affects culture, the way culture affects science will begin to become clear here. Then we talk about conservation laws, thermodynamics, and the arrow of time. Did any of you, except for MJ, know that the only place in physics where time had an arrow before modern quantum mechanics was in thermodynamics? Few people really knew that, because a lot of people never took thermodynamics. That's right, the concept of entropy. Very remarkable thing, because this is not what you call a fundamental law. It's a law that comes about by many bodies moving around and doing things, and lo and behold, time has an arrow. Time goes in one direction. Okay, next is electricity and magnetism, Maxwell's symmetry and unification. The idea that two different things could be unified into one. This is a way of thinking. It's a cultural change that comes about in the mid-19th century. Then Einstein and everything else. And quantum mechanics takes three separate ways of looking at it, because it is a fundamental change in the way people think. And it really takes a lot of time for that to become developed in the world of physics and become part of what we do. Because without it, your cell phone doesn't work. Without it, your airplane doesn't get from one place to the other. You know, that's the satellite navigation system. And then, because this is a college of optics and photonics, I'm going to take the time to tell you about 5 experiments that define modern optics. The other reason is that a lot of this stuff is all about the development of models and theories, and I'd like you to see how important experiments are, even though experiments are built into all of this stuff, because all those theorists couldn't do theory if they didn't have experiments that they didn't understand, and therefore they wanted to explain them. Here's some experiments that had to be done before you could have modern optics.
I had a comment.
Yeah.
If it's allowed.
Sure.
In terms of experiments in modern optics, there is an excellent 1-minute video, it's on the web, of Feynman describing in 1 minute, or maybe it's a minute and a half, what is the essence of science.
Oh.
And you can Google Feynman 1 minute essence of science or something like that and find it pretty easy. Of course, the web is full of comments, but it's a beautiful example of Feynman in action.
Uh-huh.
And with his wonderful New York accent and all this kind of stuff. But basically saying is that how do you do science? You write down equations and you do an experiment. If the experiment doesn't, the equations don't fit the experiment, the equations are wrong, then you have to start over again. But anyway, I recommend it.
Okay, that's great. By the way, this is where science exists. All the models and theories are only because they can help you understand your experiments and perhaps predict what will happen when you do another experiment and lead you to other things. And Feynman probably got it right much better than any of us could. Time, the past and future histories of the universe, is these last 3 are to kind of expand your way of thinking, give you senses of where things are headed, and give you a sense of why do we do these sorts of things? Why do we wonder about these far out things and what effects they have on the way we as a society, the world, the human race, worry about stuff like that, and broaden your thoughts, because these things are really affecting our culture. And that's one of the main points of this whole course, is to get you to see where we're all headed, not us particularly, but the society in general. Okay, so some more stuff. Because there are controversies, and this country is particularly weird about controversy, particularly controversy over creationism and science, creationism and evolution. There was an incredibly weird event that took place in Pennsylvania early in the 2000s, where they tried to sneak something called intelligent design into the school system. And there was a big court fight over it, and there was a dramatization made over the trial that took place. And I'd like you to see that, and we can discuss it. So one evening, after we've talked about scientific controversies, we'll have some pizza and sit down and watch that dramatization and then discuss it. Because it had to go to court and have a big trial. The show is called Judgment Day, in case you're interested. And it'll be a very interesting evening to see how ordinary, nice people got caught up in this fight over whether or not intelligent design belonged in the schools. I'm not going to tell you all the details, but it's a fascinating story. And then, after March 22nd, when we've finished with quantum mechanics, I would like us to get together to see the play Copenhagen. It's a play about Heisenberg visiting Bohr during World War II, when Germany had already conquered Denmark. Bohr is still in Copenhagen. Heisenberg is leading the atomic program in Nazi Germany. And he goes to Copenhagen to talk to Bohr, who was sort of his father figure in science. And the play is about what might they have talked about. It's an incredible drama, and it leads to some very interesting questions to discuss about what might have happened, what could have happened, what should have happened, and what are the responsibilities of scientists when they are conducting really high-risk science. Okay, I mean, Heisenberg was working towards an atomic bomb. And Bohr, when he escaped from Denmark, wound up working in the Manhattan Project in the United States. So, question, is there anyone here who cannot come on a Wednesday evening? Think carefully, because if no one raises their hand, we're going to make the show on the 3rd and this show on the 23rd. Oh, whatever you like, 7 o'clock. Okay. Okay, so we'll order the pizza for 6:30 and then have the show at 7. Does that work? And I guarantee you the pizza guy will be late, because they always send somebody with the pizza who doesn't know anything about the campus and winds up delivering it to the Fine Arts Building or something like that. So we'll order it for 6:30 and we'll have the show at 7. Okay? And you can bring your boyfriends, your girlfriends, whatever you want. I always get too much pizza anyhow. And the dean pays for it, so it's okay. Okay. Now, some questions to look at, some questions about all of this. How old is the universe? Okay? Anybody got a guess? If you're a creationist, it's 6,000 years. Okay, is there any creationists here?
Yeah, the Bible never says how old the universe is.
That's right. It doesn't give time. By the way, the sun is made on the 4th day, so there's really no idea how long the days were before. Okay? So the days before could have been much longer. Okay, but how big is it? Except for that very, very bright star, which happens to be in the picture, everything you see in that image is a galaxy. And every one of them has 100 billion stars or more. That's really a lot of stuff. It's only 4% of the matter in the universe, but it's a lot of stuff. Now here's an image. Oh goodness, how did I get that on there? How do I get rid of this?
There's a double arrow thing to the right of the bar.
Oh, there?
Yeah, in the center, just hit that.
Okay. All right, now, this is a schematic of the solar system. This big yellow thing indicates the sun if it were in the picture, and it would be a curve like that. It's rather large, okay? This little blue dot is Mercury, Venus, that's the Earth, that little spot there. That's Mars, Jupiter, Saturn, Uranus, and Neptune. Did I get them right, MJ? Okay. That little thing is the Earth. This is the sun, and it's a little something in one of those galaxies. So we're really not very big compared to the rest of the universe. So the question is, how do we fit into that vastness that is the universe? And are we important? Okay? Is it likely that we're important? In the grand scheme of things, are we very important? We certainly are important on this little blue dot that is the Earth, and we ought to take care of it. So part of what we're doing in this course is asking ourselves the question is, why do the answers to these questions matter, and what kind of answers are important? And so that's why we're having this discussion.
Just a detail.
Yeah.
Now, the size of the planets are kind of more or less to scale, but the distance absolutely are not.
Of course. Yeah. This picture is just to show you the relative sizes. Yeah.
Are the distances to just a different scale?
No, they're just not.
Okay, they're just not.
It's just to fit it on there at all. If they were to scale, Neptune would be out 2 or 3 miles from here. So, I mean, I'm not sure, in fact, where it would be, but it's certainly not in this room.
Neptune is about 3.5 light hours away.
Yeah. So, anyway. All right, now, let's try to define science as we get ready to get into it. Science is a method of interrogating reality, a cumulative process of testing new and more refined explanations, not an assertion of dry and unalterable facts. It's a way of asking questions, not of imposing answers. So when you go into a class and somebody says, here's Newton's law, it's the wrong way around. The first statement should have been, how do we know the way something accelerates? How does something accelerate? Well, before I know how it accelerates, I should know what its velocity is. Before I know its velocity, I should ask, where did it start and where does it end? That's kinematics. I'm working backwards. But the point is, you ask questions and then you work out the answers. You don't start the other way. So instead of asserting the facts, you ask questions. Science is a process of asking questions, not imposing answers. Okay? That's a very important difference between science and many other things that humans do. Well,
Can I add my definition?
yeah, but it's coming up. I use it.
Never mind, I'll shut up.
It's next slide. Give me a chance. Okay, so what is science? Well, science has common beliefs, and you might say to yourself, science has beliefs? I thought that was the role of religion or what have you. But it does. In science, you have common beliefs. Does anybody want to say what the common belief in science is? Does anyone know?
Our senses are reliable.
Our senses are reliable. That's a good one. Anybody else? Yeah.
Reasoning is valid?
Reasoning is valid. That's another one. Okay.
Independent of the observer.
Independent of the observer. The simplest belief is that tomorrow is going to be pretty much like today. In other words, we have a belief that we can understand something today and it will still be understandable tomorrow, that something is not going to come along and change the color of this bottle from blue to yellow between today and tomorrow. Oh, but it could, but we can understand why it changed. Maybe the sun bleached it, maybe you poured some chemicals in it or whatever, but left alone, that's going to still be a blue bottle tomorrow. Right? Don't put any chemicals in there. Okay. You want to make me look bad, you'll change, bring a different bottle. Okay, we have common behaviors, scientists do. Scientists have common behaviors. They know to be careful and safe in a laboratory. They know to, where to put things. They know how to take care of their equipment. They know how to use their computers. They know how to program this and that. So we have common behaviors. We have common attitudes. We approach problems in a similar manner. We do things carefully. We do whatever. We have common ways of thinking and seeing, as you were just saying. You just said common ways of seeing and thinking. Common modes of living, more or less. We live in the labs and in buildings like this one. We share space. We do that. We have common arts, by the way. You know what we have as common arts? We make models. We always try to visualize things. One of the most important model ever made was the benzene ring. Okay, it allowed all these hydrocarbon structures to be visualized, and people were able to do organic chemistry. Another great visualization was, say it, done by a Russian in the late 19th century. The periodic table, of course. He visualized the way the atoms fit together in some strange way, and we have this beautiful, beautiful thing called a periodic table. And we have common technology, well, science is what we're talking about, and views of the world and the universe. Okay, so keep in mind all these things that we have in common. And now, MJ, you can read your thing. Science is the subject of what can be proven wrong. The beauty of that is it distinguishes it from the fact that you cannot disprove belief. If you believe that there's, I don't know, a god of the volcano, that's okay. You can believe as much as you want. And I can't disprove that belief. But I can prove wrong the notion that when lava flows down from the volcano in Hawaii, it's going to be hot enough to melt everything in its path. I can prove that you're wrong if you say it won't do that, because I've seen it do it. And other people have, and they've measured it, and they've watched it, and it does it. So clearly, science is what can be proven wrong, and disbelief is something, and belief is something I cannot disprove. That's the distinction between belief and science. Okay? Very good, very simple definitions. Now, how does science work? Two most important questions in science is what can I know and how can I know it? This is asking the question of what are the things I can look at and study. This is the question of how can I study it? Religion and science part over the first one. Religion thinks it can know why, science thinks it can know how. These last two words. Why in religion is, well, God said it could be, or the gods said it could be. And science says, how does this work? How does the laser in here get frequency doubled to make green light? That's a science question. A religion question would be, why is there green light? Why do we see that more bright than we see infrared light? We don't see infrared light, we see green light. That's because God made the sun yellow and our eyes adapted to green light more than it does to infrared light. You can ask the question any way you like, but the difference between religion and science is in these two words. Okay? The answer to the second question is what defines modern science, meaning this question. Methodology matters as much as the question itself. How do you approach a problem to find out what the answer is matters as much as the first question. How do you get the answer? Is the approach meaningful? So methodology matters. When your advisor or yourself goes to measure something, or the advisor tells you, you want to solve this problem and do that or whatever, it makes a big difference if the methodology is right or wrong. Very key point. So, just a minute, I think I did it again. Yes, I skipped this because it's important. So what do scientists do with their data? They pull it together and form a model or a paradigm, and then what do? You test it and you test it again and again, and the methodology matters. The way you do the tests have to be meaningful or they're not meaningful. And how do you know? How do you know if these tests are meaningful? Because you go back and you check it again and again. Does anyone here remember the problem a couple of years back where people at CERN and people 400 kilometers away in Italy saw that the neutrinos were going faster than the speed of light or something like that? Yeah. Okay? It didn't make a whole lot of sense, but what they did was go back and check everything, and they found they had a loose connection. And thus they got the wrong answer, and they reported that we made a mistake, and this was science checking itself. So it really does matter to check everything and make sure you got it all right. And that's this how do you know? You go back and you test it again and again, and you make sure it was done correctly. If anomalies are found that do not fit, and that's the CERN experiment, you modify the paradigm, which means you throw away relativity, but then again, you check the experiment. But if they're real, if the anomalies are real, you either modify the paradigm or you replace it. Okay? Very important. That's what Einstein did when he had the problem of Michelson-Morley experiment. They said that the speed of light is the same no matter how you're moving. Einstein had to replace the Galilean relativity with some completely new model. Nobody liked it, but in fact it worked, and it has worked every time it's been tested. So he had to, and if ever they find a real anomaly, they'll have to change that. So, who's a scientist? Is anybody here a scientist? Or you want to be? Okay, you will be, I assure you. But you exist on the frontier, and you deal with the unknown. That's what's cool about being a scientist. So when you go home to see your parents or all that, they ask you, what are you doing? You say, I deal with the unknown. Not only can't you know what I do, I don't know what I'm doing either. So tell them that. And I'm developing tools to probe the unknown. You could have some scary music playing and all that. Anyway, but you are exploring it in a disciplined manner. You use techniques that are established and understood. You have a meter stick. It's 1 meter long. You know how big it is. You have a timer, and yes, you're measuring picoseconds and all that, but it's an established picosecond. You know what it means to measure a picosecond. And you don't torture the data to find a result. You torture the experiments to be sure the data is correct. This is what it means to be a scientist, is that you make sure the data is right before you start to mess up the model. Okay? It doesn't pay to put bad data into a model. I'm emphasizing this because I'm an experimentalist, and secondly, because all the data that goes in has to be right, because theories are only as good as the data on which they are based. So the properties of science is that experiments must be reproducible. If A gets a result in her lab, then B must get the same result in his lab. So reproducible is key. That means that the types of experiments that are being done have to be done in an understandable and reproducible fashion. So beware of the experimenter who says, I did this, I did that, and I did this over here in a special way that only I know how to do, and then I did this. It's that step that has to worry you. That's a sign of pathological science. It means that the experimenter is trying to hide the fact of the work. And when he does that, you immediately have to get nervous, because the experimenter is trying to hide something. And the results have to be expandable. You may be able to build on it, learn from it, and maybe use it as a foundation to build new structures, whether it's new materials, new designs, faster pulses, or I don't know what. But it's nice that the results add to the body of science and allow you to build on it. And what are scientists supposed to be? Isn't it wonderful if everybody would be honest, ethical, trustworthy, not biased? Now, when scientists go astray, typically they become pathological, and they come up with things that are called pathological science. The three examples I put here, polywater, infinite dilution, and cold fusion. I will get to these in more detail in the discussion of scientific controversies. Polywater was an idea that came out of Russia, that there was a polymer version of H2O. This is not possible. Infinite dilution came out of France, where the idea was that you could put a medicine in water and then dilute it many times, and it would still be effective as a medicine. 10 to the minus 6 dilution, or 10 to the minus 10, and it would still have medical effect. That, of course, was nonsense, because eventually you diluted it so much that there wasn't even a molecule of the medicine in a drop of the water. But this became the subject of type of medication that's still around, homeopathic medication. Cold fusion was a bit of nonsense that came out of Salt Lake City a few years back, that where they thought they'd seen fusion in an ordinary electrochemical experiment, and had they would have killed off a good part of the population of Salt Lake City due to the radiation that would have been generated. We'll get into all of those things later on. But you got to understand that all three of these things would, if they had been true, made the inventors Nobel Prize winners, very rich, very powerful, and of course, they were all phonies. The people had become pathologically involved in an experiment that had been totally flawed from the very beginning. And that's what you have to keep your eyes open. When people make claims that are so far out of the norm, you got to look at it very carefully. Okay. Now, science affects culture. That's what I've been trying to say. We started with some of that when I asked you about your cell phones and your cars and your other stuff. It affects ideas. People think of things like the bacterial theory of disease. Somebody had to come up with that. The separation of the air, gases in air into oxygen and nitrogen for the most part. That's an idea that leads to the understanding of there are different elements. And eventually Mendeleev comes up with the periodic table. Inventions, well, the steam engine goes from something that actually looked even more ancient than that to the high-speed trains that we use today in other countries. It changes manners of thinking, views of where we are in the universe. Other inventions. Just a little over 113 years ago, that was your airplane. The Wright brothers flew in 1903. Today, well, it's been put to rest, but there's the space shuttle. I could have put up the Concorde, but that's also been put to rest. I could have put up something else, but I didn't know what. But we have gone incredibly far in terms of our ability to travel. We've landed on the moon. It was unthinkable at the beginning of the 20th century. Changed our view of our place in the universe. And now, telephones, that's what they looked like around 1900. This is what you could imagine if you were so inclined to do, go surfing with a cell phone pinned to your ear. Okay? A bit of nonsense there, but we've changed. Science has affected our culture in several dramatic ways. And in ways that you have accepted into everyday life totally casually. I mean, this is 2016. In 1990, a cell phone was more or less half the size of your bag. And it weighed about 5 pounds. And you were thrilled to have it because you could use it to call the highway, call assistance when your car broke down. And that's about all you did with it because nobody else had such phones, and it was an analog, and it cost a lot of money to make a call and all that. But what science has done is not only do all this, but it's speeded up the process. The process of change is going faster and faster. So science is changing our culture rather dramatically. So culture, however, the bigger world outside, affects science. Right? Does anyone disagree with that thought? And it does so in terms of what kind of science is done. Half of all the money that the United States spends on research is spent on, anybody want to guess?
Defense, fundamental science.
No? You're just waving your hand, you know?
No, yeah.
National Institutes of Health.
70% of all federal funding to universities come from NIH.
Okay, that's another way of measuring it. And half of the total, though, they spend other money in other agencies, in other the institutes and what have you. So the total is half, but 70% that goes to universities comes from NIH. So if UCF is going to get in to really big time competition, our medical school has to get busy doing research. And that's the kind of game that you're in, because society thinks, and maybe rightly so, that research in the areas of medical, biological health is very, very important. So culture is affecting science. No doubt about it. Where is it done? In universities and institutes, some government laboratories. Why not? And by whom? Well, you just heard it. Researchers in universities and scientists, generally people with research training, PhDs in specific fields. And society affects how that research gets converted into technology. When does, and at what rate does, let's say, the latest integrated chip gets put into your latest cell phone, whether it gets bigger or smaller? It used to be that a cell phone was supposed to be very small. I remember going to Japan some years back, and I was marveled at how tiny the cell phones that they used was, and compared to the rather large cell phones that we had here in the States. And I wondered, why didn't we have such little cell phones? Well, who knows? Maybe their culture wanted smaller cell phones and ours didn't care. Well, nowadays, cell phones are as big as that, and everybody seems to be thrilled with it. Yeah, you can, play games, you can check your bank account, you can, check your email, do all that stuff on a personal administrator or whatever it's called, personal PDA or something. You have all sorts of things to do on your cell phone But what's been lost in the process is the smallness of it and the ease of carrying. I mean, there was a time when a cell phone really did fit in your palm. Anyway, that conversion to technology is determined by the culture you're in. And how is that technology utilized? Okay, is it utilized for good or for ill? Is the utilization effective or not? And how is scientific knowledge diffused? Is it kept as much as possible secret? Is it diffused to the general public? For example, the United States and Russia still hold smallpox bacteria. Though smallpox has been eliminated, you have to ask, why are they keeping any of this bacteria? And they both say, well, if ever it reoccurs, we could deal with it and so on. But just keeping it at all has to make you people, all the people, kind of nervous. Why don't you just get rid of it altogether? It's a question. So the society culture is holding on to information which, maybe we all want to know about. So, okay, those are issues. Now here's an example of how culture affects science. World War II, the scientists in the United States were aware of the Nazi atomic program. Remember that the first fission of uranium to produce fission energy took place in Germany in 1939. The United States was not yet in the war. It was the end of 1941 that the United States got into the war. And one of the first things that happened was that a letter was drafted and Einstein signed it. It was sent to Roosevelt, and he started a project called the Manhattan Project, which would eventually lead to the making of nuclear weapons. I don't know if any of you are familiar with that little bit of history, but that is a way that science is affecting culture. It led to nuclear weapons. Those nuclear weapons got used twice and not ever since, because the world learned how awful they could be. Problem is, since then, a variety of nations have since obtained nuclear weapons, and we have lived in the time since in fear of their being used. Throughout that period of time, since 1945, or 1948, when the Soviet Union got its nuclear weapons, the Soviet Union, the United States, and then, of course, Britain already had its nuclear weapon. France got its. Eventually, China and other countries, there's now probably, 15 countries in the world that have nuclear weapons. And you can see what happened recently. North Korea set off a nuclear weapon. Nuclear weapons are beginning to spread, and they're not in the hands of countries who you can truly trust. And so it affects how nations behave. And how do you deal with countries like North Korea, where the leadership is not always rational, and you can't for sure trust them? So you have science affecting culture, not always in a good way. Culture affects science. Well, after World War II, there was huge funding for atomic and nuclear science. The money was just thrown out the door to anybody who said, hey, I'm a nuclear scientist. Oh, here, take the money, go do something. I wasn't there. I was still in elementary school. But that was what I heard from people who were there. Scientists were lionized. They were the greatest thing since sliced bread. Eventually, however, the image of scientists, especially in the movies, became nerds, geeks. They were awkward and they were unpopular. And what else happened is, and I didn't put it here, but maybe someday I will, you found scientists becoming the evil scientist who was going to destroy James Bond and kill everybody in the process and so on. They also became millionaires and billionaires, as you know, by the owners of Microsoft and Apple and what have you. And they also became sponsors of the next generation scientists. They've begun to put out scholarships and fellowships and all that. But it's this business here that I always find very annoying. And that is, it's kind of up to us scientists to break that mold and to let people know in whatever way we can that you may think this, but, and I love the bumper sticker, you may call my child a nerd now, but you'll call him boss in the future. And we ought to expand on that notion that these are the people who are going to rule the world. They're the ones whose intellect and whose intelligence and creativity is critical to the future. And that's part of our job. So whenever you get a chance, whenever your life leads you there, make the point that scientists are not that, that we have something very critical to offer.
Some of us are.
Well, we might be, but don't make that the point. Anyway, for next Tuesday, this is a little fun and games exercise. Using what you know as scientists, design an extraterrestrial intelligent life form. All right? What properties must it have, and what capabilities and what technologies would it have to have for us to realize that it was an intelligent life form? Okay? Note that here on Earth, we still can't determine how intelligent some species might be. Okay? So, in other words, it's a little exercise in you using what you know to think about what would an intelligent life form, an extraterrestrial life form, have in order for you to know that it was intelligent.
As in like the bare minimum capabilities for us to recognize that?
Well, yeah, walk through that, something would come through that door, or I would lead something in through that door. And you would have to tell me whether it was intelligent or not. What would you look for? What features, what abilities would it have to have? So we'll have a little exercise on your part, just to stimulate your thinking. You're not going to get graded on it. It's just something for you to think about. I mean, here on Earth, there are a lot of people who suspect a number of different animals are intelligent, and I don't doubt it. My dog knows a few things too, but I wouldn't qualify it as being technologically intelligent. It's just knows a few phrases like when to go out and when to eat, you know. But if I were to have an intelligent critter, how would I know it's intelligent? How would I know it's an intelligent being? What features would it have to have minimally to be able to be intelligent? Unlike the alien in the Alien movies, that critter, which is like a big insect, wouldn't pass the test. But what would an intelligent alien have to be? So give it a little thought, and we'll take a few minutes next time to talk about it.